Zurab. Maybe you remember it was in Genova. And the talk lasted 2 hours and 50 minutes. So let's see, hopefully we have no upper bound, but...
No, okay. I see there.
So please, Zurab,
I'll try to be short. Okay. Thank you, Luca, to you for your suggestion to give this talk about something. Luca had something in particular in mind. So I thought that, yeah, it would be a good opportunity to come back to Axions to talk something. I have given title something like Fantastic Animals, Where to Find Them, but okay, this is sort of... So, essentially, it's not talk, but it's my thinking flow, which I will try to share with you. So interact, please, directly at any moment when you have concerns. What should be the place of the axion in relation with other physics, which you see around? Because I have sort of ideas that physics is a unity, and everything should not be just ad hoc created by some particular problem, but it should be unified with something else, common vision of the... So let's try to collect the best things which we have in the understanding of physics of the time being, in spite of the crisis which we have today, because related to standard is working too well, the shades ways beyond standard model to understand, but I hope everyone here believes that there is some physics beyond standard model, otherwise one would not talk about axion, right? So, I believe that axion is not that minimal step beyond standard model in ad hoc purposes, but it has, if it exists, of course, because experiment is a final point which should find this animal somewhere, and we can only guess now where is the correct place to find this. So, what about, I will talk around here. It is relation of the Peccei-Quinn symmetry and axion to concepts like family symmetry, supersymmetry, grand unification, and mirror sector. Okay, some sort of too much, but I will try also, by the way, unify them with each other, that they are not really separate entities. So, to start with, just let's briefly remind what is axion from the very naive point of view, or why it's needed. Okay, I will not make the things which were repeatedly spoken here. So, in QCD, we have this problem when I will not write all terms which I have to write in the Lagrangian, but I have to write mass terms of the quarks. This can be U, D, and whatever it is, and plus theta term I will not write with G square S 32 pi squared, just like that. So forgive me for the imprecision in the schematic presentation. So these are two relevant terms. Here is implied that quark masses are in the canonical normalization, gamma 5, Q bar gamma 5 Q are eliminated from this writing. So essentially we get Dirac equation, and there is this term. So, and it creates a problem because essentially it will tell you that you will have in the theory, which is defined without this term as a vector-like theory, with no parity and CP violation, you will get parity and CP violation. And this term you can discuss whether it is theta coupling constant. You can think that in context of some string theory and supersymmetry, it emerges from the imaginary part of dilaton, and is phi the Lagrangian part. If Giadwali would be here, he would tell us that no, it is an integration constant, irrespectively you write this term or not, it's there because you have to superselect vacuum state, and it's up to you. Whatever, it is translated in whatever language, it will be the same thing. So you have to forget that, you have not to forget that this term will cause the gluon condensate of GG dual, which will cause these observable effects. Essentially, first effect which you would see in the strong interactions, after all, is decay of eta into pi's, for example. But experimental limit from that, it's not that terrible as from the neutron electric dipole moment, and out of that, this electric dipole moment is less than 10 to the minus 26. Then you will make sort of rough conclusions that it's number which is characterizing this vacuum state. It is less than 10 to the minus 10, small number. And about its origin, we have no good understanding because even anthropic principle, it hardly can be used because there is no way. It will be just a kidding, because if theta 10 would be 10 to the minus 3, for example, it would not change story of our life, and experimentalists would be happy to discover these funny CP violating effects, and we would know something fantastic, but unfortunately, it's not the same case. Why the quark masses should be tuned like that with electron mass and so on. It's a different story. So I have some half an idea that maybe it can be also semi-anthropically related, but I will not talk about that, which, by the way, gives you something right number here, but it's too complicated. If you will ask at the end or privately, I'll try to show.
So just tell us in which context.
No, it's a completely different context, and if I will start with that, I will mix up with the rest, because it's without axion. So instead, I want to concentrate on something with axion. So what could be the way out of this problem? Everyone knows, if one of these quarks would be massless, which means that you have a chiral U1 symmetry, global chiral U1 symmetry in the theory, then would be no strong CP problem, okay? And this we know also, I will not go further. But it's not completely necessary that this U1 chiral symmetry is realized in the unbroken phase because of one quark is massless. You can have this chiral U1 symmetry also spontaneously broken, and in this way, you could still solve the strong CP problem, okay? Which means that here, quarks are written. But when I'm writing here quarks, I do not imply necessarily U, D, and so on. For me, there are no weak interactions here included. I have this prejudice away. Imagine that I'm born before the standard model, but by some historical time change and so on, first I discovered QCD. And then later on the weak interactions. They are too weak that I do not know even their existence. So in that case, I could say that in principle, there could be a big amount of quarks, and this sector of quarks can include some quarks, let me call them Q and Q bar, which, let me call them Q and QC, and further on I will use chiral language of the non-period. They get mass because of breaking some global symmetry. So this is case. You transform this by some phase, and you compensate that by the complex field which is here. And at the end of the day, you get Goldstone particle in the spectrum. Even the up and down quark masses are non-zero and so on, they are hardly peaks there. These additional quarks, they get masses because of spontaneous symmetry breaking. Essentially, what you will get here, that you have to add here to that system also something after substituting vacuum expectation value, call it VPQ times exponent of E alpha times VPQ. If you write, let's put here square root of 2. So this is vacuum expectation value, this is Goldstone phase. You put it here, and then you will see that the phase of this field is free. So what is needed to define what is the structure of the quark mass phases? This phase will appear as additional and to there. So essentially, you all remember this sort of formula that effective theta, which you essentially make observable, it is some theta, which perhaps is formally written in Lagrangian, but you have to add here argument of the whatever mass matrices you have here. Okay. So this part will create you this phase. So it means that here, essentially, you are adding something to this number, which is n times phase, because it means that these particles can be not one, but several. N is this, which defines. And this phase had to be eliminated. It becomes dynamical degree of freedom. It should have shift symmetry. It should be related to Goldstone. And then your system makes theta term dynamical value, which always makes minimum where effective theta will become there, because we have to add here this Goldstone field, and it minimizes all effective theta. So all we know. And this n, whatever will appear in the general axion scenario, it will be simply related to something which is anomaly of this chiral symmetry with respect to the QCD. So there should be quarks. And that's it. It is what I have written here, something which we call KSVZ axion. Okay, and nothing more. It's irrespectively whether I'm talking about standard model or not. I can always add something which gets mass from something. And this vacuum expectation value can be as big as you like, and then you are only constrained by phenomenological conditions, because it does not mean that this axion interacts only with heavy quark sector, because we are writing then the triangles like that. This is current of this U1, and here you will get this GG dual because of this anomaly, and then you can link it with the light quarks as well, and you know that essentially only one thing will be that such an axion will not interact two electrons that efficiently. And it can be created instead if you make here also photon lines, which you can also not forbid if these particles have electric charges, and then you link it to electron, but with F and F dual correspondingly, and you will create also some suppressed coupling of axion to electron. So this is this phase, because this Goldstone field, which should be precise symmetry in order to completely eliminate effective theta term. It should have exact shift symmetry and should not be broken. And if you go to standard model, then it gets only into some complication, because in standard model, you know that I'm still writing relevant terms. You have YU, let me write EJ, UCE, QJ, H, plus the same thing for these are Yukawa couplings. These are complex. So it means that even if I'm standard model, I can always turn right-handed U quarks in order to make this matrix fully diagonal, whatever this phase I have to remember. Then this is generic matrix with complexity, because effect of that, it is complexity in the CKM mixing matrix, which passes through. So all is complex. And here one can think, but it's the same situation. Here we have H, and here we have H. So this field contains some phase, and maybe I can use it. And not because of double reason. First, you could say that this phase here, this field is complex conjugate to that field. So whatever phase will appear here, this phase will appear here with negative sign, and simply they will cancel each other, even if it would correspond to Goldstone, which means that even SU2 symmetry would be global and not. And another is that simply in the reality of standard model, this phase is eaten up by gauge field in order to make massive Z. So forget about Z, but by the way, I started my physics sometimes when it was just very fresh. And so-called Weinberg-Wilczek axion appeared at that moment, which suggested why not to make two Higgses, so that this phase and this phase can be rotated in the independent manner. Then you really have additional global symmetry, because apart of vector-like symmetry, when this and this transform in the opposite phases, and it's just a fermion number conservation, you can make chiral symmetry here, absorbing the net phase in this field, and here in this field, but this is not complex conjugated to Z, and then you have to put the condition on the 2 Higgs doublet potential and try to get, you have two parameters, vacuum expectation value here, vacuum expectation value here, total vacuum expectation value, it is sum of these two. Then, by these two fields, so it means that you have to eliminate anything from the Higgs potential of two fields, which is not Hermitian. Only in this case, you have possibility of independent phase rotations. So, then some combination of these two goldstones, let me call it AU and AD, which will be proportional to VU times V plus Vd times V, so it's a cosine and sine of some angle, will be absorbed to make mass of Z boson, and orthogonal combination, which will be Vd times V minus Vu times V, would be goldstone, which will remain, so it will show up here as a net effect in this term of the phases, and it will make an axion, which is called, Weinberg called it at that moment, I remember simply because it were the very first papers which I had to study, a part of the strong CP problem, and to speak on the seminar in our institute where I was just master thesis. Weinberg called it axion, and Wilczek called it Higglet, because it was some sort of remnant of the two Higgses. And now everybody remembers them as axion. Higglet, I think, is forbidden name, but Pierre remembers perhaps that it was Higglet also called at that moment, right? Weinberg called Higglet. I remember that it was Wilczek. We can check it, because I remember that it was Wilczek. Maybe you are right. Maybe I just mix, memory something that is correct, but sign is a terrible problem in physics because you make a mistake, but sometimes irrelevant, sometimes irrelevant. Okay, it has double name, and then everyone knows them as axion. Okay, it was fantastic axion because it could be discovered experimentally just tomorrow. And it had no problems with astrophysics. As a matter of fact, sun would be insensitive because axion would have mass of MeV and would be safe from all points of view, apart of the phenomenological point of view. So it was quickly eliminated because it was enough not to make new experiments, but just to look the data already existing on whatever, and to discover that there is no place to put for any choice of two vacuum expectation values. These windows quickly disappeared.
I have a question. So, as far as I understand, there was not a unique observable that ruled out.
No, it was a combination of up quark or charm quark or S quark, kappa P, axion, and B, and so on, whatever it was analyzed at this moment. People, they could look on just existing data, so it was eliminated pretty quickly that nowhere they could see the trace of such a MF particle, which would give you some electron-positron burst or two gammas or whatever, because it's very quickly decaying particle. Essentially, it had to be something like pion, but at MeV mass, okay? And it's difficult to hide. But it was fantastic. For astrophysics, it was fine. If it would remain like that, nobody would have problem of star cooling or so, or it would be before supernova, perhaps, of course. Now, the way out was something which was really very ad hoc, which is called another. So this axion is a KSVZ axion, as it's known. It's one of the prototype model. Another is the SFZ. One would say, why I will put here, I can put another singlet introduced to link it is between here and here. I get Goldstone from another one. Actually, it would be dominate. So essentially, this symmetry is not broken by the relative phase of these two. But it's broken with some other field, which is linked by something like S square HU HD. And then think whatever, but you still get a hidden axion where you can bring scale. A part of that causing some chaos in the two Higgs, and you have to fine-tune things. And for one Higgs, fine-tuning problem is bad, and for two Higgses, it would be worst. So now, what would be easiest thing in order not to go to the historical part and just directly to modify all this without introducing two Higgs doublets? Okay. By the way, supersymmetry introduces two Higgs doublets. You can ask why I'm not using it. Because in supersymmetry, even if I'm introducing two Higgs doublet, already by phenomenology I'm forced to write in superpotential so-called mu term, which will not allow to have independent phase rotations of HU and HT. You can say at some moment it was even possible that this mu is zero, but then it's excluded because of Higgsino, neutralino stuff. So supersymmetry does not want to realize it as it could be. Anyhow, it would be stable, but there is no symmetry reason why I'm not writing this term, okay? It is allowed only. And essentially, it is a problem, actually, that mu is not zero, but you have to create it, and by some reason, it is a supersymmetric parameter, but it has to be of the order of electroweak scale or supersymmetric breaking scale at the end of the day. And then appears question which people coin as a mu problem. If you solve doublet triplet setting problem, why you manage to make zero the doublets, even in the supersymmetric theory where technically you can make it stable, that it still appears by some coincidence of the order of supersymmetric breaking scale or quark and lepton masses. Okay, so maybe I will come back to this later on. So one possibility to immediately make this, let me leave here Higgses H and H bar, or it means that if I'm talking in the supersymmetric context, I'm still writing mu term between this and that. But instead, I declare that whatever I'm writing here as Yukawa coupling constants, they are fields. Essentially, I have here upsilon, it is some field which has two indices and follows to some symmetry. M, it is some scale by which Yukawa coupling constant becomes normalized in order with this respect to field. I'm writing higher order operator. And then I'm writing simply okay, you can imagine what will happen here. But in order to make the things easier, let me shift at that moment to something which would be grand unification. And then I will come back here in order to write things easier. In grand unification, what I have? If I'm talking about the system, even with these axions, by the way, maybe I will make this excursus. Here I have HU, HD, I have introduced two Higgs doublets. What about leptons? I could write about leptons, some another coupling, and in principle, I could use the down one, or I could introduce for leptons still third Higgs doublet. So I could have for all of them independent phase rotations, and I would have that in my games there would be two Goldstone particles. One would be axion, which would take here the relative phase of these two, which would take here for eliminating theta term. And here, another Goldstone will come, who would be essentially massless because it would have only SU2 anomalies, and Anselm has introduced sometimes this particle, call it Arion by the Axion correspondence, and it is simply massless particle which could have even enough long-range interactions. It could have sort of gamma Arion transition effects easily without suppression because of axion mass and so on. And in principle, one of the Alps, which is completely massless, or it could have some small mass because of explicit symmetry breaking, whatever you can imagine here. But it is sort of prototype model that variety of Goldstone bosons could be, if you proliferate Higgs doublets, big. Now I'm against of such a big proliferation. Instead, I want to shrink the system in order to be more predictive. Imagine what would happen if I would try to discuss all this problem in the context of SU5. So in SU5, essentially, I have families as a 5-bar, which contain DC state and L state, lepton doublet, and 10 E equal 1, 2, 3. Okay? Which contains UC, Q, and EC states. And essentially, these couplings which are written here I could play different things. I could introduce, for example, separate symmetries. This is transforming by some SU3 of up quarks only. This transforms by SU3Q. So I could have here a general global symmetry of these terms as a U3 in 5, all types of fermions which I could have. For leptons 2, and for quarks, okay, 5 types of fermions I have: Q, UC, DC, L, EC. If I'm putting here, I can shrink all this symmetry to 2 U3 factors, which would be U3, which transforms 5-bar, and U3, which transforms 10 states, because they are all sitting in the same multiplet. Okay, it's what concerns of some global symmetry of flavor, which I could introduce here. But if I will go to SO10, then all this is sitting in something which is 16, and essentially it remains only one U3 symmetry which could transform all this 16. And this is sort of something which is right-handed neutrino. And what I can write here, just going directly to the grand unified context, I simply, it will be just the composition of that what I will write. It will be 10 times 10H, and here I would write 10 times 5-bar H. Okay? So, about these fields. Now, I suppose that this is the same field here and here, and I am taking gauge symmetry, which is this, but only its SU part is gauge. Because I don't want to take here for mixed anomalies which can appear there. And only SU3 anomaly I can cancel by introducing by some spectator fermions, equivalent amount of triplets or other representation, so I can handle it easier. But this will be a field, essentially it is one of my first works for 82 or something like that in the beginning of 80s. I was still a PhD student. So, what these fields can be if these are transformed in the triplet. So, these tens are triplets of this symmetry, and these are also triplets of this symmetry, of gauge symmetry. So, triplet times triplet, it means that these flavon fields can be only in the representations which contained in the triplet times triplet. So it means that it can be only sextet or anti-sextet or triplet. Let's put here 2 upper indexes, symmetric combination will be sextet, and anti-symmetric combination would be triplet, just lowering by epsilon down. So, gauge symmetry is SU3, but observe here that this term has bigger global symmetry. because it has U3 symmetry. So essentially, I have here of these terms SU3 times local multiplied onto the U1 global. And observe that by definition, this global symmetry is a chiral symmetry. SU3 is also chiral.
I have a question. The chi is a triplet, then in the scalar potential you can write a cubic term.
Sure, yes. This term has this does not change what you say now. This term has U1 symmetry. Question is whether I can break this symmetry. It's the same history, whether I could put here two Higgs doublets and the Higgs potential write some term which would break this symmetry. And it would be enough to write simply HU cross HD in square. This term would break U Weinberg-Wilczek axion. It's non-Hermitian, it's not conjugate. So you have discrete symmetry, but it kills your Weinberg-Wilczek axion. So here, essentially, I have to say, this axion, because my purpose, sort of, or subconscious purpose was that I don't like to postulate global symmetry. I want to have it as accidental symmetry from gauge principles. Because only one thing which we know, that any global symmetry which we see in our life, which are needed, by the way, lepton number, baryon number, and so on, sometimes we had to justify and postulate the symmetries. But it wasn't enough to write standard model. We understood that these symmetries are accidental symmetries of standard model because no renormalizable term or marginal operator would give you possibility to break the symmetries, and you can codify them only in some effective operators. For them, you have to declare that they emerge from some physics at that scale. So it enters with new scale, and we know, for example, that to break lepton number, you need this operator. And here you have to write this mass scale. You call it lepton number breaking scale. And fine. The scale is big, then you get neutrino Majorana mass. We know neutrino mass more or less now. We know that the scale should be something close to grand unified scale. But essentially, it more or less gives you indication where this new physics could appear, irrespective of all that. Here also, but here there is an operator which essentially, independently whether we are talking about sextet, you can make something like determinant of Xi, which is sort of cube term with dimensional constant in front, and you can break it in Higgs potential. But you can still avoid it by introducing, for example, like in the case of Weinberg-Wilczek axion, some independent, some discrete symmetry. I could say, I have sign reflection symmetry, and I could kill. After all, it is small parameter from the point of view of the naturalness principle of Hooft. Putting it to 0 increases symmetry of the system. So you are getting global U1 symmetry because these terms are symmetric by definition. So essentially, if you by some way forbid this term, and imagine now if I would have something like not 3 families, but imagine that I have 10 families. Oh, in that case, you would not ask me that question, right? Or you would ask me, but...
I think you can also do something using a rectangular Flavor symmetry.
Of course, of course, of course, of course, of course. This is technical detail anymore because things are born from here. It's a question of not model building, but just way of thinking. What is direction? Direction is the following, that I want to have a gauge symmetry, and by the gauge symmetry principles, I will get global U1 symmetry as accidental symmetry. Just like lepton number appears in the standard model or baryon number. Okay?
So you were saying that both are chiral, right? So then I guess that you need some fermions in order to consider its anomalies. Don't they also imply that the U1 will also be anomaly free?
No.
Or can you do it
No.
in a way that
No, they can be completely neutral without these UN charges. No, does not imply. Does not imply, no. Actually, you know very well that if I start to make without theory, which is contained in the non-abelian theory, where I'm guaranteed that no anomaly will be there, the question of anomaly cancellation is a headache, and you rarely find good solution, right? So that's why I don't like ad hoc UN factors, for example. In any case, this is the way, but what is the particularity of axion which will be introduced in this way? Here it is conjugated with the idea that actually hierarchy of fermion masses and mixing, it is related to the structure of this flavon field. You can imagine, for example, as a toy model in which you have one sextet and very natural configuration for its vacuum expectation value. It is something like that. It breaks symmetry, which is, let me write here, SU3 times U1 global to SU2 times U1 global. Substituting this wave here, you get here that 3,3 index is locked and third generation gets mass. Imagine that next field in the symmetry breaking chain, it is a triplet which has vacuum expectation value towards first component, orthogonal to Z. First component in the language of the upper indices, two-index representation, it means 2, 3 component. Here I have V2 minus V2, but it is a triplet. By epsilon, it transforms in the antisymmetric part. So, V3 scale, the symmetry breaks down to here. At scale of V2, it breaks down to the U1 global. Generators are mixed, of course, during this breaking. It's not the same symmetry which was written here. It's like in standard model, you are mixing with the, and global symmetry always remains. It's imagined that sort of you have something like standard model, but U1 gauge factor has zero coupling constant, and photon, whatever it is, it's just left with a gold stone after that. So, at that scale, it breaks down to the symmetry, which acts only on the first family only. And at the last scale, you can introduce another triplet, which has towards third direction vacuum expectation value. And it breaks this symmetry down to nothing. But it is already Pechequin symmetry at the language, because if I will look that this scale is bigger than that scale, and essentially neglect their contribution in the Goldstone particle, so this will be global symmetry, which acts on the first generation. Essentially, it mixes this Pechequin field, first generation to second generation. So, axion is sitting here. It corresponds to that scale. And if I normalize it to the GATT scale, for example, this scale is grand unification scale, then top quark has to have order 1 mass, so biggest vacuum expectation here is a GATT scale. But this scale is 3 orders of magnitude smaller should be. I'm coming up somewhere as a 10 to the 12 GV or something like that by this normalization. What is interesting, because it is just in the ballpark where I could wait that axion is a dark matter. And second, that it has particularity. This axion is a flavor-changing axion. So now it is a lot of activity on the flavor-changing axions and so on. It is sort of axion which appeared in the accidental way, but it had to be in this context, flavor-changing axion. It has to cause something mu E alpha decay or K to P alpha decay and so on. And it is also scale more or less 10 to the 10 GV was at that time scale which was excluded by such a transition for this construction. So more or less it has something behind, and at least I know the physical scale on axion. It is related to some other physical scale, which in this case is a grand unification. And It is not so direct election, but another case of this particle was that I could use it for the generation of neutrino mass in the same context, and having this unification and LSAR sitting together with it, essentially this operator would also emerge at that level, and I could call this particle also Majoron. So this was a particle which was not only axion, but it was a familon, and it was a Majoron at the same time. So I do not need to proliferate Goldstone bosons for each occasion here and there. It's just one particle who plays this role. Now, I have 15 minutes, maybe 20. Started. Huh? You can leave. Don't impose your to others. Okay, so I could talk about the mirror step or whatever. Okay, question of accidental axion. It can be by gauge symmetry. Recently, I have done some work with Stefan Bogorsky when we played this game as a toy model with the Frogat-Nielsen mechanism, one symmetry, and so on, but it's irrelevant. Let me say something more new, or maybe very old, but still. How I could come to this concept from the grand unification without even applying to family symmetry. Maybe I can just multiply the things on each other.
Also take the blackboard.
Okay. Let me take this blackboard. You see, you don't give me 2.5 hours like in Genova's. Imagine that, in principle, here in the game of the constructing these operators, I could use grand unification fields. Only that, living at the level of SU5, grand unification field, which is 24, it is essentially a real representation. For simplicity, I sometimes impose on the discrete symmetry a sign changing. It's not relevant. But even in supersymmetry, it's more important. If I will want to use this term, I cannot really so easily assign to it Pechequin charge. By the reason that I need in superpotential this term, which is cubic. Otherwise, I would have too much massless colored particles in the game, which would ruin my, because it would have too big symmetry, okay? If in other ways I want to generate vacuum expectation value to this field.
But with supersymmetry or without supersymmetry?
No, with supersymmetry.
With supersymmetry.
With supersymmetry. Let me go just directly to the point. Without supersymmetry, if it's real, I cannot. I have to introduce two fields, but I have to make them complex artificially in that case. Or I have to invent some locally one symmetry and play between two local symmetries once their combination is there, and it becomes too ad hoc. So here, this term I cannot. Now we can ask, let's go to SO10. Do I have here some good candidates in order to have complex representations? What I used here, I used that this flavor group, which was SU3, it had complex representations. That's why I got the symmetry also as additional, as accidental, because I need complex representations for group, for gauge group, and then from them I can stem complexity of the U1 there. So in SO10, generically I use something which are also very similar for the breaking of SO10 down to standard model, which are 45, 54, and so on, but I can use the 16, paying some price for the R parity, which still need be to introduced by hands. Okay, in principle I can do, but still it will not be end of the story, because I have to generate from the way vacuum expectation of 16 and 16 bar. I have to introduce both of them. And at the end of the day, I have to somehow avoid mass term, which is relating one to another. Otherwise, I will get the same story like mu term in the standard model. And then I don't know how to generate vacuum expectation value of these two guys. So I will go to the best model in this case, till I have 15 minutes that I can end up. So mirror symmetry, I will talk other time. SU6, which is the model. Okay, supersymmetric. What it implies? In SU5, you have these fermions, 5 bar and 10, you have H and H bar, which are sort of triplet and doublet, and here it was asked about doublet-triplet splitting, how it comes out that it is, you need something to be orbifolded and so on, which I don't know by which penalty you can make this. Anyhow, problem is doublet-triplet splitting, because you can make these doublets massless, you have to make these triplets at the grand unification scale, and you have to also solve the mu term that these doublets will have mu term which will be of the order of supersymmetric breaking scale, will not be introduced ad hoc. So is there a model which can do this naturally? So it is called SU6. What it does? It implies that you have also, like in SU5, a part of sigma field, which is here in SU5 and in unit Z. And doublet-triplet splitting is related to, you essentially have to introduce this term between 5 bar and sigma. Otherwise, you will not manage to split doublet from triplet, because only this can make triplet heavy. And in doublet, against cancellation of mass term of doublet, you have to substitute the vacuum expectation level here. So in triplets, it becomes large, and in doublet, it cancels. And it is a procedure which makes fine-tuning absolutely necessary in order to make triplets heavy. Now, what can be done here? How this can be all circumvented? It is essentially fermion multiplets, which I can call 6 and 6 bar prime, which is the decomposition of 27 of E6 theory, which is a maximal subgroup of the E6 theory, okay, this 27, plus 10, plus 1. It is this. I don't need this one, so I can introduce this one for neutrino masses, whatever, but this is what I need. So this is anomaly-free set. If you go to decomposition, it is 5 bar plus 1, 5 bar plus 1, and so 15, sorry, 10. And it is 10 plus 5 bar, 5 prime. And this one with that makes massive particle when SU6 symmetry is broken. So I just simply reduce to the one family SU5 theory after baking SU6. It's like 27, you remember that it's the composition to the SU5. It is 10 plus 5 bar plus 5 plus 5 bar. This is extra 5 plus 5 bar in 27. So essentially, this will appear here in this way. And you have sigma, which is now 36 in the dimension. It is adjoint, like here. Only that you don't write this term by some symmetry reasons. So here, this term is forbidden. What appears in this case? These 6 bar and 6 bar, they do not talk each other. H has vacuum expectation value, for example, towards 6 component, it breaks symmetry. SU6 local symmetry down to SU5, okay, fundamental representation, whereas adjoint representation breaks symmetry to SU4 times SU2 times U1. And let's count the Goldstone degrees of freedom. Out of that, you get Goldstones, which will be all absorbed by gauge fields of the SU6, by superfields, by the way, because I have to talk. And you have nothing, because all degrees of freedom which you have here, phases, they are absorbed here, and you are reducing yourself to SU5 theory. But not having this term, essentially, all the 36, which contains 24 plus 5 bar plus 5 plus 1, has a global symmetry which is SU6, because this field does not know that local symmetry is broken, it still keeps a global symmetry. Essentially, it was before. This is modeled by me and Giadwali. Before, it was Anselm's model, which is simply just postulated the symmetry without having a motivation, but complemented by a singlet, I could, in principle, build. Okay, intercross of these two symmetries, it means that goldstones will appear in the representation for 2 of this group. Out of that, 3, 2 will be eaten by gauge fields of SU5, which are X and epsilon bosons, but 1, 2 will remain, and 1, 2 and 1, 2 bar. H and H bar will remain as a Goldstone superfields, which would remain completely massless. Then you will switch on supersymmetry breaking terms. You will write here something like M3 let me call supersymmetry scale M3 times superpotential term, which is sigma cube. So we'll break supersymmetry, you will get shift of the vacuum expectation value of this field, which substituting backwards, because goldstones are sitting here, and there is no triplet. Triplet is eaten up by gauge fields. So you are getting mu term, effectively, of the order of z directly from here, as well as you are getting also b mu term and so on. Nothing will remain. And all this of the scale. Supersymmetry breaking scale, supersymmetry breaking generates you mu term as well. So it's not only one bonus. What you have here, you have also possibility to play with fermion masses, because Higgs knows that it is pseudo-Goldstone boson originated from some extra global symmetry.
It's just you wrap up and then maybe you want to continue.
I still have time.
Yeah, it's 5 minutes.
Even formal time. Because
It's 5 minutes to 3.
I'm just looking on that at the moment from where I started. If I have 1 hour, I can use it, or I can stop here.
Say a bit in advance.
Huh?
What should be remembered from this? What should be remembered from this? What should be remembered from this?
What should be remembered? It should be remembered the following, that now I have 2 fields, vacuum expectation values, which I can generate with independent phases. I wanted to make this. For that, I have to explain how the fermion masses are generated, because being Goldstone, you can generate it fermion mass only by terms which break this extra global symmetry, which is SU6 times SU6. And essentially, you can make it U6 for these complex representations. And you can realize axion, which will live with Pecha-Equin scale at the grand unification scale. And it will appear without any price if I will make all-order solution of the hierarchy problem in this theory, because this theory has particularity. In order to generate fermion masses, I have to write Yukawa couplings between this and that, in where H and sigma, or H bar and sigma, all participate, because I cannot write only terms, for example, 6 bar times 15 times H. Because, first of all, in H, Goldstone is living with a small piece, but it is occupied because this field gives mass to 5 bar and 5 from here. And it gets heavy fermion. So I can use them for the fermion mass generation, but I have to write all heavy operators apart of one, which is top quark. For top quark, by some reason, if I have some multiplet, which is 20, fully antisymmetric representation, I can write only one term where I can generate out of this term mass of top quark, because I cannot write mass term of this 20 multiplet. It's pseudo-real. Okay, it is some particularity for which one needs another things to explain. But important is that when I'm writing the operators H and H bar, they have liberty to have independent phase transformations. But this concerns on the singlet part of the sextets, because these Higgses, which are 6, they contain singlet plus 5 bar. Goldstones are sitting here, but these ones which are sitting in the H and H bar, which are sextets, they have liberty to change phases independently. Okay, I can make this by construction. And I have sort of axion where in the structures family field is substituted by grand unification field which breaks SU6 theory down to SU5. And I have liberty of phase spaces that this field which is sitting here, this field which is sitting here for up and down quarks, then I can rotate with independent phases. So symmetry breaking scale should be something like 10 to the 16, which is not maybe that perfect situation for solving the dark matter problem, so it should be matched by hand. I have to introduce something. I have to tackle the problem after inflation, before inflation, Berezhiani phase transition at this scale has happened. I have to start something with wrong perturbations, no? Isocurvature. And I'm pretty close, I believe, to this, which is called axion black hole superradiance, 10 to the 16 GeV. But still at the margin, and maybe it can be another interscale, but it is just an example. When solving a big bunch of the problems, I'm just coming to the possibility to have also accidentally one symmetry inside without imposing it. And it tells me what should be scale of Berezhiani from the other physics. So in one case it was family symmetry, and in another case it is grand unification, okay? But it's truly fixed by that scale, sort of. And it's sort of not ad hoc symmetry, but it is part of construction in this case. So that was the philosophy, since Pierre does not give me more time to talk. I will quit here.
So questions?
Maybe can you tell us a bit about the mirror worlds that you were going to discuss?
Okay, mirror world, it was simple thing. If I have two copies of standard model, and I have Z2 symmetry between them, in principle, I can have common axiom between these two. Imagine that I'm making here Q, U, C, H, and let me make just an axiom SM without playing with the flavor group and so on, plus S bar or S, M, Q, U, C. It can be also a flavor group, for example. Now we can imagine that there is common flavor group, by the way, for anomaly cancellation, the same as U3. This is sextet or triplet. And I'm assuming that my fermions of usual sector, they are triplets. But of that sector, they are anti-triplets of this group. So with respect to the SU3, theory becomes vector-like, and it is the easiest way of cancellation of anomalies, because anything which I introduce, even in a supersymmetric way, if it is sextet, it is anti-sextet, and they are talking even their contribution. And apart that, because of the Z2 symmetry, I have full cancellation of the D terms of this group, independently how this flavor group is broken. And it is essentially, I can make full solution of the minimal flavor violation in the supersymmetric theory. No D-term contribution, nobody can do that. I have done it 25 years ago, okay? So, now, apart of this anomaly cancellation, now what it can be? That by some reason, if I talk about sort of initial theta term, which is by vacuum superselection, here and here, they are by some reason equal. Fermion mass matrices, because of the similarity, they will be simply the same structure. So if I will cancel theta term in one sector, it should be canceled automatically in another sector. And here it starts the discussion whether it is possible or not, because I have to select independently theta terms here and here, same, because if they are simply vacuum properties, why I have to make them equal from the very beginning? But imagine that I'm just generalizing symmetries, they are equal. And the next step, I'm making the simple step that this scale is bigger than this scale. Electroweak scale in that sector is bigger. It will make then QCD scale also in the sector because all fermions become heavy. Infrared pole we will get earlier then because renormalization group evolution from the symmetry limit will be faster. And essentially Axion will solve strong CP problem of this sector, which is heavier, but it will solve also by parallelism if it exists. And I think this parallelism should exist if these two groups will appear as a subgroups after decomposition of bigger group after spontaneous breaking. Otherwise, of course, I have to add that essentially, yes, this part of argument of YU, YD, and so on, they are similar in two sectors. It is true, but it's not guaranteed that vacuum should be anyhow parallel. If they will emerge from the same original theta term, which is written as a Lagrangian of the full theory, which includes this product, then it would be more plausible. But what would happen here, that axion would become heavier. So for the same scale, for example, 10 to the 6 JeV, or 10 to the 7 JeV or whatever, I can make axion if electroweak scale is, for example, at 10 TeV or something like that, I can make it as heavy as few MeV. And it would become safe from the many points of the astrophysics. I could make pretty heavy. And in this case, it will not be axion, because axion relation, mass relation to scale relation will be violated. This product will be equal to the MP prime FP prime, which I can say that it is lambda square prime, more or less. It was lambda square. So if I will make it many orders of magnitude bigger, essentially I make axion heavier, and this is different axion. I called it Axi-Dragon at summer because we had with Rubakov in parallel the same way, this way of the thinking, but he used different breaking. It was not a standard model, but he started from the same grand unification. Actually, we had some communication at this moment. Only he has written the paper somewhat earlier. My paper is better. Okay. So then it can have not implications for dark matter, but it can have implications for some violent phenomena like gamma ray bursts or supernova explosion, because such axion you can produce into the supernova core, but it will not cause destruction of the limit of supernova because they can destroy it into the electron-positron pairs. Inside the mantle, it will be like piston, which in supernova deposits energy from inside to outside and makes rejection of the mantle. And instead, it's some type of supernova which has not bigger outside part of its helium alpha. It can make more relativistic expansion. You can make its gamma ray burst and such a thing. So in any case, it has different function. It was axion or Axi-Dragon of astrophysical interest anyhow. But still, I don't know whether this relation, which I like at all, and by that reason, in all the reviews, you show this axion line, and the relevant area for this axion, which is from 10 to the 10 to the 10 to the 12 GeV, it is touched by experiment, which is called MEDMAX. And it will be very important what it will show up. I hope that something will be found there. If not, then one has to think about alternatives and so on and so on. But in any case, okay, that was. That you can make also this relation, and not wholly, and you can think about it. Then there are the variations on the term, maybe the symmetry is not broken at all. Then what would happen if there is massless quark? Essentially, axion will not disappear. How you have to treat Pecheykov symmetry if quark is massless? Axion is still there because the mechanism of the Higgsing of three forms has to still work. But axion, it is something which we will call eta prime. Okay, so then you can play the role that maybe here there is no symmetry breaking in the mirror sector, and instead you will make eta prime there because quarks remain massless, and by parallelism it will also transfer to solution of our sector and such things. Then you can choose your variant of the model. Important that in principle you can touch this relation for the axion mass. I think Luca, you tried to make it even lighter. He tried to make it lighter. Okay. Okay, I would prefer heavier, but if you want to serve some other experimental purposes, it's okay.